Hey everyone. In this video, we will be talking about Zorn's Lemma. I'm calling this part 6.5 because Zorn's Lemma is something that I think a lot of people watching this might be familiar with already, but also a lot of people watching this might not be familiar with. So it's something I definitely need to explain. But if you've seen Zorn's Lemma before, because it's applicable to a lot of different fields of math, if you've seen it and are familiar with it, you can safely just skip this video. But if not, let's talk through Zorn's Lemma. So first things first, Zorn's Lemma is usually defined based off of something called a poset, which stands for a partially ordered set. But for our purposes, we will be for our purposes, we'll be applying Zorn's Lemma to collections of sets. And as a result, in order to avoid having to explain what a poset is, I'm just going to define Zorn's Lemma in terms of collections of sets, because that will be how we apply it. However, Zorn's Lemma is more applicable than what I'm showing it. It applies to many, many more cases than just this. But like I said, it'll be easier to explain this, and this will be the actual use case we need it for. Okay. So in order to even state Zorn's Lemma, we have to define a few things. So first, we'll define a chain as follows. So let script f be a family of sets. So basically, intuitively, this is a set of sets, right? But I'll call it a family to hopefully distinguish it a little, but it's basically just a collection. I have a bunch of different sets, and I'm grouping them together. Okay, so now the actual object we'll be thinking about here is script C, which is a subset of script F. And so that means it's a sub-collection of sets. So F might have 4 sets, and C might be some arbitrary 3 of them, right? Okay. So let F be a family of sets. C is a chain if for every, and now S and T in script C. So S and T are sets. We have, and then S subset T or T subset S. So a chain is, a general collection of sets does not have the property that any two sets, one is a subset of the other. But we're saying that for a chain, a chain is some sub-collection of these. I'm giving you F, and then a chain is a sub-collection of F, where for any two sets in that sub-collection, one is a subset of the other. We'll build some intuition about this later, but we'll have to say one more thing. A chain is upper bounded if for, I don't know what to call, I guess I'll just call this, so we'll just, for some F in the family, not necessarily in the chain, but just for some F in the family of sets, for all S in the chain, S is a subset of F. Okay, so the idea is an upper bound is a set that is a superset of everything in the chain. Okay, if you don't have the intuition for this yet, I'll work through an example at the end of this video, but these are the two things that we need to state for Zorn's Lemma. Okay, so now Zorn's Lemma itself. So for a family of sets F, if every chain is upper bounded, then a maximal set exists. And by maximal, I just mean that maximal, I'll put in parentheses down here. So maximal just means that for every f in f, I guess m is maximal if, and then I meant to put this here, for all f and f, m is maximal if for all f and f. You know what? I guess that's the beauty of MS Paint. Okay, so m is maximal if for all f in f, f is a subset of m. So it's some object, or rather, I've said this backwards. That's not true. Sorry about this. So an element is a maximum would be a superset of everything in the set, of everything in the family. But what we just want is that there's nothing larger, right? That there isn't an element larger than this. And importantly, what we can't do is just, obviously if I take the union of everything in the family, that would still be a set. But that may not be in the family, right? Or that would still be a set, and that would definitely be the largest possible set you could get from the sets in the family. But that may not be one of the sets of the family, right? So the importance is that M is actually an element of F. And that, it's an element of F where no element of F is larger. Okay? Hopefully that makes sense. If that doesn't make sense, the next thing I'm going to do, if that doesn't make sense, again, you can just skip the rest of this video. If that doesn't make sense, then the next thing I'm going to do is a short example of proving something extremely obvious in a roundabout way to employ Zorn's lemma. But again, if you think you understand all this, just go to the next video because you'll see Zorn's lemma being used there. Okay. One thing to say before we move on is that Zorn's lemma is basically an axiom. And those more knowledgeable would know that Zorn's lemma is equivalent to the axiom of choice, which is one of the axioms of set theory. And we'll prove that later on. But what that means is that it's no different to assume, there's an axiom that is directly equivalent to Zorn's lemma, so we might as well have just assumed Zorn's lemma as the axiom and then proved the axiom. So there's no use trying to prove Zorn's lemma. This is just, we basically treat this as an axiom. Okay, so let's do an example and talk through a basic proof of proof using Zorn's lemma. So let me make sure. Yeah. Okay. So let's let F is all sets only using 1, 2, or 3. And the first thing I want to do actually is draw a picture to show what the inclusions in this set look like. So here's the empty set, and then of course here's the set 1, here's the set 2, and then here's the set 3, and then here's the set 1, 2, here's the set 2, 3, and here's the set 3, 1, and then finally here's the set 1, 2, 3. Okay, and then I'll add in these arrows. So the empty set is a subset of 1. In fact, the empty set's a subset of everything. So in theory, I would have to draw arrows to every single element. But I'm not going to do that for brevity. Just understand that this picture is transitive, right? So, if empty set is a subset of 1 and 1 is a subset of 1, 2, then empty set is a subset of 1, 2. You get the idea. And then, 3 is a subset here and a subset here. 2 is a subset here and a subset here. 1 is a subset here and a subset here. And then all of these are a subset of 1, 2, 3. Okay, so I have this ridiculous mess of arrows. But now let's unfurl this a little further, and let's try to work through and understand one instance of our definitions before Zorn's lemma. So this here is a chain. So a chain is basically if I follow these arrows along any path I follow along these arrows will be a chain, right? So this empty set 3, 3, 1. For any two of those three sets, any two of them, one is a subset of the other, right? It's a strictly increasing sequence. Another chain might be, empty set 2, 1, 2, 1, 2, 3, right? Okay, that's a chain. And then, if I go back to my chain, empty set 3, 3, 1, then the set 3, 1 is an upper bound on the chain. And this is an upper bound on the chain because the chain is finite in size. In general, if the chain is infinite, we would need an upper bound. If I have an infinite chain of sets, my upper bound would need to be something outside of the set, right? But for finite sets, it's really simple because the upper bound is just the largest element in the finite collection of sets. That's your chain. Okay, so hopefully that is a better example of what a chain is and what an upper bound on a chain is. And now, what the maximal? There's only one maximal element. In general, there may be multiple maximal elements, but one maximal element in the set is the set 1, 2, 3, because 1, 2, 3. There's no set above 1, 2, 3 in F that contains it. So Zorn, we'll try to, obviously, it's really simple to understand why for the family of all sets that use only 1, 2, and 3, why the set 1, 2, 3 is a maximal element. But we'll try to prove that this set exists using Zorn's lemma now. Okay. So our proof will have to look like something along these lines. So we're going to let C be an arbitrary chain. And what we need to do is prove that, or what we need to, I'll even write this just to be explicit. We want to show C is upper bounded. Okay. So, how do we do that? In this situation, it's simple because it's finite. So let's make some very basic argument to show that this set is upper bounded. So I guess I'll call this set T be the union of every set in the chain. And now, right, importantly, we need to argue that T is still a member of the family. So, since all C in C only use 1, 2, and 3, T also is in the family, right? So T also only uses the elements 1, 2, and 3. Right, so obviously the union of a bunch of sets that only contain 1, 2, or 3 must produce a set that only contains 1, 2, or 3. And then obviously for all C in C, C is a subset of T. So T is an upper bound on script C. Okay. And then finally, I'll change color here just for cinematic effect, I guess. So since every chain is upper bounded, Zorn's lemma guarantees a maximal element. And Zorn's lemma, of course, doesn't give us I didn't actually prove I didn't prove that 1, 2, 3 is a maximal element. I just proved that there is some maximal element, right? But so in a way, I think I'm not sure if it is technically non-constructive, but in a way, it is, because it guarantees the existence of a maximal element without necessarily giving you any method of describing what it is. But I don't know. I would need to look at the proof of Zorn's lemma from the axiom of choice to see if Zorn's lemma was proven non-constructively. But either way, the point is, we're not really concerned with what the maximal element is. We're just concerned that there exists one. And this seems like a very weird, it seems like just a very weird sequence of. I don't know how to phrase this. This seems strange and useless, but it's actually very useful. It's actually extremely useful to have maximal elements in a lot of situations. So this is something that will come up and keep coming up. Okay, well, I'm going to stop it there. Hopefully you gleaned some better, if you weren't familiar with Zorn's lemma, hopefully you gleaned enough insight that when we go through the Zorn's lemma proof in the next video, it'll be comprehensible. So hopefully this example, this much easier example of a proof with Zorn's lemma was helpful with the sort of technique we'll try to play through, which is, showing every chain is upper bounded and then using Zorn's lemma to conclude that there's a maximal element in the set. All right, so I'll see you next time, where we'll prove we'll prove a statement with Zorn's lemma. That should be episode 7. So anyway, thanks for watching, and I'll see you guys around.